Now the second type of ideal that we're going to look at, or the last one, the other one, is a maximal ideal. So let's take a commutative ring. So let R be commutative. Well, let's say a commutative ring. And let's let M, subset of R, be a proper ideal. We say that, and just to be clear, this is like a fractor M. We say M is maximal if what? Well, if no proper ideal of R properly contains M. Which is to say, if J is another ideal of R, such that J is strictly bigger than M, then it must be that this subset or equal to, it must be the or equal to part. Then J is everything. So M is like a peak of proper ideals. There can be ideals smaller than us that we contain, but there's nothing that contains us besides the trivial ideal, which is all of R. Okay? So maximal here means maximal using the order given by, well, pre-order given by subset containment. So that's what a maximal ideal is. And we're going to use a fact that, well, I'm going to state a fact that we may or may not need actually, but I'm going to state a fact, and it's the following. It's a consequence of a lemma called Zorn's lemma, but I'm just going to write it as a theorem. Any commutative ring has a maximal ideal. And that is beyond the scope of this class, and we may not need it, but I just want to state it. So so they always exist. So every ring has a maximal ideal. And so some examples for a moment is, well, if F is a field, we saw that F has no non-zero proper ideals. So the ideal 0 is maximal. Because there's nothing in between 0 and F. There's just no ideals that are non-trivial when you have a field. In Z, prime ideals are maximal. So ideals generated by primes are maximal. So for example, 5, 7, 11, and so on are maximal. And the reason being is if I had a prime, so let's say P prime, and it was contained in an ideal, well, it's a principal ideal domain, so it has to be contained in a principal ideal. This would tell me that P was in the ideal generated by M, which would tell me that P is a multiple of M, but they're not allowed to be equal. So this has to be like an honest multiple of M. K can't be 1, for example. So this would contradict P being prime, right? Unless M is 1. So that is, we get all of Z. So in this case, prime ideals in Z, so ideals generated by prime elements, which we'll see for Z, being generated by a prime element is equivalent to being a prime ideal. those guys are also maximal. Okay? And this is actually a fact that we're going to look into a little bit more detail when we have just not a general commutative ring, but a PID. So here's some examples of maximal ideals. It's sort of nothing in between you and the whole ring. I guess let's also do, while we're here, real quick, an example of a non-maximal ideal. So let's stick with Z. I claim that in Z, the ideal generated by 4 is not maximal. Well, in fact, let's not do 4. Let's do 6 to make it a little more interesting. 6 is not maximal. In fact, I had you work out Hasse diagrams, and you saw that 6 is kind of contained in the ideal generated by 2, but it's also contained in the ideal generated by 3, and Z is sort of at the top of that. So 6 is not maximal because it's not a peak. It sort of is under, it's like if you're climbing a mountain, right? You have two peaks here, 2 and 3, and you're like on a saddle. You can choose which way to go. So so it's not maximal, as 6 is properly contained in 2, which is properly contained in Z. It's not equal to Z. And similarly, or 6 is properly contained in 3, which is properly contained in Z. Another example, an interesting example that we'll come back to is if our ring is Z adjoint X, the ideal generated by X is also not maximal. And actually, this is kind of an interesting example. And so I'm going to do the next video on this example. But this is going to be an example of a non-maximal ideal, and I'll show you why in the next video.